each presentation will be of 40 minutes, and we will also have 10 minutes for each presentation of Q&A. So for the Q&A, I think you just raise your hands, and then we will give the word to people to get their questions in. First of all, I would like to remember to everyone that we have a RADNEXT deadline for submitting your proposals. It's coming very soon. That will be at the end of this month, 30th of September, I think. So please, everybody, remember this deadline. Of course, we will have thermal neutron beam lines available, but of course, many other type of beams, and we will have many other neutrons and heavy ions, ions, protons, and many more types of beam within RADNEXT. I think we can now start the webinar. First of all, we'll give the floor to Manon from ILL. She did all the job to organize the webinar. So if Manon can introduce the speakers for us.
Thank you, Carlos. Good afternoon, everybody. So our first speaker will be Robert Baumann from Radiosity Solutions, and also he's also a research scientist at Texas University at Dallas. So he is the one who discovered the effect actually of Boron 10 effect because of thermal neutrons in the electronic components. So he will tell you more about this. So Robert, I think the floor is yours.
Okay, thank you, Manon. Very good introduction. And Carlo, thank you for organizing everything with Manon. So today I'm going to try to give kind of a basic overview on the impact of thermal neutrons and integrated circuit reliability. So it's going to be very basic, but hopefully for Paolo's talk, it'll be a good introduction. So as an outline for today's talk, I'm a history fanatic. So one of the things I want to show is a short history of the discovery of the boron 10 problem. And although Manon gave me credit for discovering it, actually long after I published my works, I found two older papers where people had mentioned the boron 10 problem. So I'll give a link to those if you want to find the original. I wish I had known about those papers. It would have saved me probably a year of research. But anyway, this is one of the things in science. We repeat experiments many times before people appreciate that things have changed. Then a very quick overview on the terrestrial radiation environment. This is basically for any students or people that may not have experience. There's fundamentally three mechanisms. So I'll just talk very rapidly, just mention them. And of course, the focus will be on thermal neutrons, which is one of the mechanisms, particularly with the reaction between thermal neutrons and boron 10. So then we'll kind of cover a little bit in detail why boron 10 is so bad for electronics. Then we'll consider how it sneaks its way into the semiconductor processes. And there's various processes that are used for normal fabrication where boron gets introduced. And of course, boron 10 is a naturally occurring isotope, so it also gets introduced into the semiconductor process. And then to end on a good note, I want to consider mitigation. So how can we reduce the effect of the thermal neutrons and basically reduce our failure rates? And then finally, we'll conclude with the need for thermal and high energy neutron facilities and standards.
Excuse me, Robert. Do you want to share some slides?
Are they? I was sharing.
Yeah.
Let me. You can't see my screen?
No.
Okay, I thought we had it done. Let me. Oh, someone changed the screen. That's what it was. Let me see if I can share now. Okay. Can you see now?
Yes.
Okay,
Perfect.
good. Yeah, I think when Carlos switched screens, it unshared mine. So, okay, let's see. I'm trying to get full screen here. Can you see full screen?
Not yet.
Okay. Okay, there we go.
Okay.
All right, so sorry about that. All right, so the short outline I went through verbally, so I won't read that again to save time. So as I mentioned, one of the things that I'm kind of a big fan of history, particularly, you know, history and science. A lot of people kind of view science as a constantly progressive, you know, endeavor where everything builds on what was done, you know, in the previous day or year. Unfortunately, that's not really the situation. And on the right-hand side, I show a banner with the basically this kind of revolutions, or this concept of scientific revolutions, and how they progress in a very nonlinear fashion. So what I show in the plot in the middle is basically this concept that science, in fact, does progress linearly for a while until you hit a crisis. And a very good example kind of in the last 50 years or 60 years has been, you know, going from classical to quantum mechanics. A lot of the classical physicists just thought it was garbage. They were like, you know, God doesn't play dice. How can you have probability functions? And so it took a lot of experiments and calculations to basically convince the scientific community as a whole. So typically what happens is you have a crisis, and by crisis, the meaning is that something can't be explained by the normal scientific understanding of the time. A lot of work happens, maybe some revolutionary or seemingly revolutionary ideas are presented. Initially, science pushes back. The conservative group of scientists will say, no, 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 this can't be correct. And then finally, enough experiments are done, or enough simulations, or enough math, and enough people see the results and realize, yes, indeed, things have changed, and therefore there's the so-called paradigm shift. And the author here talks about basically extraordinary science. So these are discontinuities, so very large changes. And again, I point back to the one that is probably one of the biggest ones, is going from classical physics to quantum physics. So finally, everybody accepts that. And then you progress along normal science for a while until you reach your next crisis. And the reason I bring up Thomas Kuhn's work is it kind of is legendary work on how science progresses. And he gives a lot of historical examples, which are really nice. It's a good read. So I recommend it to anyone. And I wanted to kind of give that as the theme of today's talk, because my investigations into boron 10 and indeed thermal neutrons kind of went through this same crisis mode, and then finally a paradigm shift with the whole industry. So I promise that there won't be too many slides with a lot of text, but this is one of them. I guess like any good history book, we have a lot of writing. So the paradigm when I joined Texas Instruments in the late 80s was that every soft error is caused by alpha particles, and these basically come from contamination in the VLSI processes and materials. So by paradigm, I mean everybody knew that, all the managers knew that, in all the companies, everybody was kind of nodding their heads. And I will mention that Jim Ziegler's work on cosmic ray neutrons had been published also in 1979, but in his work, he was kind of saying, well, neutrons may be a problem in the future as we scale down devices. And indeed, he was correct. But the work that really caught people's attention was the alpha work that showed clearly that alpha particles are a big problem, particularly in DRAMs. This led to a lot of improvement of materials and reducing uranium, thorium, and other radioisotopic impurities in the packaging materials. So that's kind of the environment that I was in. And the problem was we were doing things and improving things, and we still saw the field failure or system soft failure rate of our DRAMs was very high. And we improved. So for example, I went through all the packaging materials, basically looking for a so-called smoking gun. So what is the hidden or unknown source of alpha particles? Because we had looked at all our materials, and we were in sub parts per billion. And so we shouldn't be having such a high failure rate from alpha particles. I even worked with the design team to tweak our DRAM process to get the sensitivity lower. And when I tested with alpha particles, it was 10 times to 100 times lower. But yet when we would put them on field test, basically they would have the same failure rate. So at that point, I started realizing there's got to be something besides alpha particles causing problems. I did discover that some of our I/O circuits had a noise problem, so we eliminated that, but we were still having a high field failure rate. And so this is where I finally, I found Ziegler's work and a couple other works on the high energy neutrons, and started worrying about that. And in parallel, because I was doing so much neutron activation analysis, I realized that boron 10 had a really large cross section. And as we'll see, that it had kind of a bad effect when it absorbed a neutron. So this was proposed kind of in the early 90s. We kind of kept it as a trade secret, as all good companies do. So we didn't share it with the world until 1995 to 2000. We published this. And it took probably another 5 years before the entire industry was kind of aligned. So that was the big paradigm shift. So soft errors, now the realization was that soft errors observed in both memory and SRAM and logic are caused by alpha particles, of course, high energy neutrons and thermal neutrons. And as I mentioned earlier, I just want to be very clear here. Again, in the late 80s, you had to go to the library and look up works. And so you always had to divide your time between research and actually spending time in the library. I'm very sorry that I was unable to find these papers. I didn't even know, where to look, but I did find these papers later through the internet, so much easier to find them. And so the one on the left is basically the earliest I could find where people are talking about thermal neutrons damaging electronics. And this was basically an empirical demonstration that boron 10 with thermals was causing gain reductions through displacement damage on bipolar junction transistors. And then basically 10 years later, the Fleischer paper was basically the first theoretical calculation showing that boron 10 and thermals could possibly dominate soft errors, particularly at high altitude, was the conclusion. So again, I would love to say I was the first, but these two guys came before me. So I just want to set the record straight. History is important. Okay, so no more talk of history. This is, again, just a calibration, so everybody knows when I refer to high energy neutrons or thermal neutrons or alpha particles, there's fundamentally three mechanisms that upset terrestrial electronics from a soft error point of view, and potentially hard error as well if you have latch up. So high energy neutrons are from cosmic rays. They're protons converted to neutrons and other things. By the time you're at sea level, it's mostly neutrons. The neutrons of interest are generally in the range, I say 10 MeV here because that's kind of been the JetX standard. We'll talk about that a little later. In fact, things start happening at about 1 MeV, but the most of the events that we see as soft errors are generally in the 10 MeV and above. And that's, again, the neutron energy. Of course, some of the neutrons will have more interactions than others. And there's a whole class of neutrons that have had many interactions and hence are thermalized, or their kinetic energy is at basically thermal energies, so 0.025 eV. And of course, there's a distribution, so it's not just one energy. And these are interesting because by themselves, they can't displace ions. All they can do is nuclear reactions. And so as we'll see, it turns out that with boron 10, there's a very bad nuclear reaction that causes a lot of soft errors. And then finally, I just show it because it's the third mechanism. Alpha particles have been a concern for a long time. They still are a concern, especially if you introduce a new material. You have to make sure that the uranium and thorium and daughter product impurities are very low to the sub-part per billion purity levels to make sure that this is not a problem. And here, alpha particles don't really do any nuclear reactions. It's direct ionization. Okay, so the cosmic ray neutrons, as the name implies, they are from a cosmic ray protons, which are incident on the Earth at a very huge range of energies. And depending on the energy, you get different reaction rates. But in this cartoon on the right, I'm just showing that typically the protons get converted to neutrons and other particles, muons, as well as protons. But by the time you get to sea level, down at the bottom here, you're mostly neutrons, okay? And this curve on the left from Ziegler's, one of Ziegler's papers, this is a later paper, but this curve was actually introduced in 1979. We see the neutron spectrum. It turns out there's a lot of muons and this may be a potential problem in the future if critical charge continues to fall. There's a smaller distribution of protons and pions. So in general, everybody agrees, at least for technologies today, neutrons are the primary concern. So what does the spectrum look like? Basically on the right-hand side, I'm showing you basically have 3 peaks, and the peak we're going to be focused on today is the thermal neutron peak. As you can see, it's a little smaller than the other 2 peaks. So we have peaks from nuclear evaporation, as well as the higher energy neutrons causing cascade or spallation reactions, usually with the ejection of neutrons and protons with a few recoils. And so again, the main consideration with thermal neutrons, and I should mention, you notice the dotted line in the middle. This is kind of the limit for elastic silicon recoils caused by neutrons. So this is the billiard ball effect. Again, elastic reaction. The neutron comes in with enough energy to break the bonds of the silicon and then ejects the silicon with some kinetic energy. So if you set kind of the minimum kinetic energy that you care about that will create 0.5 femtocoulombs of charge, you're talking about 85 keV neutrons and above can cause this. So below that, basically what I'm saying is, at least for the elastic recoils, you're not going to get them, at least in silicon, or you'll get them, but all they do is produce some phonons and very little charge. So from an electronics point of view, we don't really care. So the thermal neutron peak, again, the red one, we're only concerned about inelastic reactions, basically where the nucleus absorbs the neutron, gets excited, and then does something. And as we'll see, boron 10 does something very bad. On the left-hand side, in the blue, I'm showing kind of, and take these to be very rough numbers. They change in a very large way with altitude and latitude, as well as to some small extent with solar activity. And so you'll see the thermal neutron flux at the top is about 4 neutrons per centimeter squared per hour. Typically, the 10 MeV and above terrestrial neutron flux is considered to be about 13 neutrons per centimeter per hour. And if you extend the spectrum and say, well, we think that there's problems even at 1 MeV, then that's about 20. So you can see the thermal neutron flux is a bit lower. Now there's things that can increase it, and it varies quite a bit more than the higher energy, because at thermal energies, neutrons are very easy to scatter. So you can have either shielding or focusing of the neutrons. So the flux varies quite a bit. Even a rainstorm or snow can modify this. And just before I go to the next slide, I'll mention in passing that these are based on New York City sea level. And this is basically the reason that's picked is it's kind of the standard baseline as discussed in the JEDEC JESD 89 standards document. So again, the flux can be very different depending on your location in the Earth, but this is just a standard value based on a specific location. All right, so just kind of in a snapshot, why boron 10 is different than all its neighbors. Here I include a list of thermal capture cross sections for neutrons of thermal energies. And basically the red line is our boron 10. The green lines are basically everything else that you can find in a typical integrated circuit. And so as you can see very clearly, boron is very effective at capturing neutrons. In fact, it's at least 50 times higher than the next highest cross section. And for a lot of the bulk materials, it's more like 1,000 times. So if you throw neutrons at an integrated circuit, the boron will be activated much faster than anything else. There's another particular property. So all the green ones here, basically when they capture a neutron, they get into basically an excited state. So I'm showing this in the diagram above the plot here. This excited state is typically released in the form of gamma ray emission, multiple gamma ray emissions, to get the excited nucleus back into a metastable or stable state. So while gamma rays in large quantity can certainly cause total dose effects and occasionally possibly generate enough charge to create a soft error, generally a single gamma ray is going to go is very penetrating, which means it doesn't have too many interactions, which means that the probability of a soft error from gamma rays is generally very close to zero. So all these green ones, essentially, we don't really worry about from a soft error point of view because they're just generating gamma rays once they get excited. I do note that gold does have a non-zero fission cross-section. It's below 0.1 on this scale, so it doesn't even show. So if gold fissions when it captures that thermal neutron, obviously that would be a soft error event of concern. But again, you're a million times below the rate that you would see for boron 10. So again, boron 10, very high cross-section. On the right-hand side, the reason boron 10 is problematic, unlike all its brothers and sisters, instead of just getting excited and giving off a gamma ray photon, actually the nucleus fissions into two pieces, and we basically get a helium or alpha particle, and we get a lithium, so-called lithium recoil. So basically it's what's left of the nucleus when it splits. Both of them have a relatively large kinetic energy. And as you can see from the table below, the alpha particle has 1.4 MeV and the lithium 0.84. If you're used to seeing alpha particles from impurities, typically the emission energies are 4 MeV to 10 MeV. So it may sound like, oh, well, these are very low kinetic energy particles. Why do we care? It turns out that you're very close to the Bragg peak. So in fact, even though they can only travel a few microns, so in the case of the alpha particle, maximum range is 5 microns. And in the case of the lithium, which is heavier, higher LET, so it loses its charge more quickly, 2.4 microns. So it's a very localized phenomena, but it can generate tremendous amount of charge. When you consider that most electronics today have a critical charge below 1 femtocoulomb, in fact, maybe below 0.1 femtocoulomb, clearly any of these events occurring will cause a problem. I mentioned here, this table is from Auden's recent work in 2020. I highly recommend it. I think it's a good overview of the problem. They talk about the integrated circuit as well, so it's a good reference. She also includes this branching, or it's another possible reaction, very similar. The only difference is that you don't get a gamma ray, so the energies are a little different. You get slightly more charge, but again, this is a 6%. So to first order, we can kind of focus on the first reaction here. And again, both of these particles can generate a lot of charge. And so that's kind of the primary concern. The neutron comes in, very high probability of this reaction occurring. We get an ionized helium, we get an ionized lithium emitted, and both of those can cause soft errors. Okay, so the curve on the left is basically showing us how much charge is injected, as well as the range. So we already went over the range, 2 microns for the lithium, 5 microns for the alpha, and the black is the charge. So this is LET converted to charge versus distance. So it's just showing you at any point on the path how much charge you get per micron traveled, and this is in femtocoulombs. So again, if you look on the right-hand side, which is a nice discussion of what the critical charge is doing in typical advanced technologies from 180 nanometers down to 14 nanometers. You can see that basically we're below 1 femtocoulomb for the last 4 technologies, at least as far as this is concerned. When you consider 7 nanometer and 3 nanometer, actually this curve continues. So we're definitely sub 1 femtocoulomb. So fundamentally what this says, in modern technologies, if you have boron 10 present in a large enough density, it's going to affect all the products you make in that technology. So it's still a concern. And the big question is, do you have boron 10 in your process? And if you do, what's the density of boron 10? That will define the failure rate. Okay, so one thing that I've noticed in papers that's kind of missing is a summary of what can contribute. So what I tried to do here, and I'll admit this is my own opinion. So if people go and look at these numbers and say, hey, wait a minute, something doesn't make sense, probably it's my mistake. But I assumed kind of maximal doping of boron. And what I'm trying to do on the right-hand column, which is the conclusion, is basically we have boron everywhere in the process. So what are the regions that are most likely to give us errors, so that if we want to fix the problem, what should we focus on first? And so I rank ordered them. So of course, boron doped glass, which is, as I said at the beginning, it's been removed from most materials, was definitely the top problem to deal with. Now it's pretty much out of the equation for modern processes. The one that ends up being a big problem now is the formation of tungsten plugs. I don't have it here just because it was too long. Also, the formation of any metal liners that are typically used in the formation of metallization will tend to be diboron based. In other words, the process chemistry used to deposit the metal contains boron at a percentage level. So it gets incorporated in these films, and you can have a fairly large contribution, kind of same order as the BPSG or boron doped glass. Now, the polygate doping can be high. People are using metal gates. So in metal gates, they might have the same tungsten plug problem. So this number could be very different. But you can see we're talking about the rest of the problems are on the order of 1% of the tungsten plug problem. So just on this diagram cross-section of the integrated circuit, I'm showing the different layers. BPSG was typically a glass layer on top of the first gate layer. So I show it here. The level of red is kind of showing the level of problem. So deep red, BPSG. As I said, because of people realizing this was a problem, also the advent of chemical mechanical polishing has enabled people to remove boron from the process. Then the tungsten plugs are here, bright red. So again, they're kind of the second contributor. Polygate might be bright red if it's metal. I assume poly here. So the doping density is lower. It's like 1%. Then of course, the NEP plus boron implants. These are the LDD, or basically, they're trying to reduce leakages at drain edges at high field regions. These are much lighter. These tend to be lighter implants, but they use very complex BF boron fluorine compounds, which are harder to mass separate. So you actually get a larger amount of boron 10 potentially fraction there. But putting it in perspective, you're still talking about a 1% effect. The next biggest one is, of course, the P substrate, and that's by virtue of since the boron has a range of about 5 microns, at least the alpha particle, you have to consider 5 microns in depth, which gives you a fairly large volume. However, even highly doped substrates, a 0.1 ohm centimeter substrate such as this, that's about 5e to the 17. So again, it gives you kind of a relative measure that's fairly low. So just trying to get in a snapshot, the key concern here was BPSG. As I said, historically, that's been removed from most semiconductor processing. And so now we're left with basically metal deposition processes. And it's not coming from the metal itself, it's coming from the reagents that are used to deposit it, typically diborane and other boron-containing compounds. Okay, so the first reaction you get from a lot of customers is like, well, why don't we just shield the neutrons? Anybody who's worked with neutrons realizes this, but just anybody who hasn't, they're very hard to shield. Of course, they're neutral, neutral, no charge, so very hard to shield in the typical way. So it's really just nuclear reaction shielding effectively. And so on the left-hand side, I show the amount of concrete required to shield both high energy and thermal neutrons. And basically, you can see that you would need tens of centimeters. And in fact, if you wanted to reduce the neutron flux by 50%, you'd need 70 centimeters of concrete. So really not a viable solution to put that kind of concrete all around a single IC. Water is a little better, and that's due to the hydrogen in the water actually has a fairly large interaction cross-section. So 31 centimeters of water. Again, unless you're doing water cooling of your devices, maybe for some advanced CPUs, you'll get some additional shielding from this. But 31 centimeters is really not going to be kind of a viable solution. One thing from history I listed as a fun fact, when I was on my path, discovering that neutrons may be the dominant thing, again, there was a lot of resistance, especially from upper management. And at that time, Texas Instruments was working with Hitachi. So we actually decided to do a field experiment where we both together made the DRAMs and we put them on field testing or basically system software testing. This is unaccelerated testing, where you put thousands of devices on for thousands of hours, and you try to get millions of device hours so you can, get a fairly statistical measurement of the actual failure rate. And initially, the Hitachi results were 50 times lower than the TI results. And this occurred first when Hitachi made the devices. And so the presumption was that, well, Hitachi's process is better than TI's. This was hard to believe because we had the same equipment set, same wafers, same production flow. So it was really hard to explain that. Finally, we swapped devices. So we were testing the Hitachi devices, they were testing our devices, and sure enough, their numbers were always coming down about 50 times lower. When we investigated or pulled apart the details, we found that Hitachi's test area was in a basement, so very large concrete basement with 5 floors above it, concrete floors, and they had a large water reservoir, several meters in thickness, where they stored water for the building, right above the test area. So just doing a few calculations, this showed very clearly that they were effectively shielding both the thermal and the high energy neutrons. All right, so I said it's hard to shield. People still wanted to shield. Certainly we did. We wrote a patent back in 1996 at looking at ways to shield the thermal neutron flux. And again, we were looking for probably a 10x reduction. 100x just wasn't reasonable. So the patent states several approaches, but 2 that I basically submitted with the co-inventors. One was to embed on the backside of the substrate and on the top side of the device. So I show in cross section here the green layers. As long as the layers are more than 10 microns away from the device layers, basically you don't have to worry about any kind of boron 10 reactions. So the concept was make a shield with boron 10. Since it's already in our glass, it's very cheap and easy to do. And we just deposit a glass layer here and a glass layer here, maybe with enriched boron 10 to make the shielding more. But very quickly from simulation, we realized that even if you do this, because you can't deposit more than a couple microns without warping the wafer, it's not really a viable solution. So one thing that popped out right away is most packaging, plastic packaging materials are either silica or alumina, and the fill of silica and alumina is on the order of 70 to 80%. Okay, and you can see in this cross section, these large nodules, spherical nodules, are basically the silica, and then you have some epoxy or polymer type adhesive that sticks the whole mess together. And so the idea was, hey, we can dope silica with boron 10 up to about 20%. That ends up being kind of a fundamental limit, solubility limit. You could also put something in like gadolinium, and certainly if you wanted to get really expensive, you could isotopically separate gadolinium-157, which has a huge cross section, many times more than boron 10. But the focus for us was really boron 10 because it was cheap, it was available. And so we did a calculation with the typical package thickness then. It was about 0.3 centimeters thick, 3 millimeters thick. So you would get a shielding that would reduce somewhere between 5 to 10x, depending on how you did the simulation. That was deemed enough, so we did that patent. Later, these authors looked at basically the same concept, but now a conformal film. So this is, I can't even pronounce that, but let's just say POSS, POS. It's a nanomaterial where you basically attach whatever atom you want to this molecule, and then you make a resin, and you can coat your electronics with this. And with high enough density, apparently they could go as high as 50% content of gadolinium by weight, which would give you some pretty significant shielding. So you get down with about 2 millimeters thickness, you get down to about 10x reduction. So shielding is possible, but it typically will add expense. A lot of companies are not willing to change their package flow. But I just mentioned that, yes, we've considered shielding. It is possible, but you do have to use either specialized materials or specialized processes to get at the shielding. All right, so this is kind of the last part of the talk. One thing that's really important, and it's been mentioned in Eugene Norman's paper here, which is kind of based off a lot of discussions we had during the JEDEC standard, is it would be great to have a facility that had both high energy and low energy, actually a dedicated thermal neutron source. So in the dream world, these are both in the same place. There are a few facilities that provide this, but in general, for example, a lot of the boron 10 experiments I did was using the NIST, National Institute of Standards. They had a cold neutron source that also had a curved beamline, so it would scatter the thermal neutrons away from the gamma flux. So you had a very pure, only, I said thermal, but they were actually cooled, so that cooler than thermal neutrons hitting the devices. So we could really look at actual, low energy neutron capture cross sections versus anything else, gamma upsets or higher energy neutrons. So again, a good high energy facility will produce a spectrum, that has most of its energy above 1 MeV neutrons. Ideally, no thermal neutrons, although that's hard to do. Of course, good dosimetry, so you know exactly what you're doing in terms of flux and fluence. A good thermal neutron source would be no high energy neutrons, for sure, no gamma rays, good dosimetry again, and minimize scattering I just mentioned, because that's a problem we've run into at some test facilities where they have a lot of concrete right near the beam port. You do get some changes in flux just because of scattering angles and things like that. So you have to be aware of that. As a last note on this slide, and to show the paradigm shift, the industrial standards always follow the understanding. So before JEDEC, most of the industry was testing only with accelerated alpha particles. So they would put their memory or their SRAM or their logic device, their CPU, under accelerated alpha particle sources, typically thin foils. And because alpha particles were already kind of tame, they'd say, hey, the failure rate's only one failure in time. This is one failure in a billion device hours. That's considered a very low failure rate, especially for a soft failure. But then you'd go and measure the same device in the field test, unaccelerated field test, again, thousands of devices for thousands of hours, and you'd get something on the order of 2,000 fit. So clearly there was a disconnect there, or a crisis. Once we started discovering all this stuff about neutrons, high energy neutrons, thermal neutrons, we were able to change or create the JEDEC spec. So in 2001, the focus of the spec was you cannot just test with alpha particles, you also need to test with high energy neutrons. At that time, I tried to push to have a chapter on thermal neutrons, but I kept it democratic, even though I was leading the writing of the spec. I put it to a vote, and more people voted that, you know what, we're not convinced that thermal neutrons is a big problem, so let's not put it in the standard. 6 years later, by popular demand, a lot of people asked us to add a dedicated chapter on thermal neutron testing. So it's kind of interesting. You go from no standard to the first standard not talking about thermal neutrons, and now we're actually on version B, but it was in version A where we actually updated the thermal neutron. All right, so 2 conclusion slides here. This is just a snapshot of sensitivities because I went over it pretty quickly. Most manufacturers have removed boron-doped glass from their processes. This is largely due to the use of chemical mechanical polishing, which planarizes the thin films. Okay, and I should have mentioned adding boron to glass reduces the flow temperature by 200 or 300 C. So it reduces your thermal processing load, which is the main reason people used it. So now with chemical mechanical polishing, like the name implies, it's a low temperature process. You don't need the boron. So people have removed it. However, you need to be aware that diborane and other boron compounds are used heavily in a lot of IC deposition processes, particularly tungsten plugs, which are very close to the active layers, as well as barrier layer formation. These are the barrier layers in the metallization. Significant boron 10 can be left in the process. And by significant, I mean at the percent level. So we're not talking parts per million, we're talking percent of boron 10. The impact can be similar to the magnitude of what we saw with boron-doped glass. Basically, although it's been mentioned in several papers, the risk of boron 10 from implants and diffusions generally represents less than 1% of the total number of events that you can see. So my recommendation is don't really focus on that area unless you have a very specialized process where you're using much more boron, basically degenerately doped boron, like 10 to the 21 or something like that. It's just not going to be a big part of the contribution to soft errors. Some industrial partners have used isotopically separated or what's called boron 11 enriched process materials, both internal to their process and for conformal thermal neutron shielding. This is another way to get mitigation of thermal neutrons to mitigate the effects. And interestingly enough, even though the work started with DRAMs, it turns out that now that we've gone to 3D cell capacitance, so DRAMs used to be planar devices and very sensitive. Once we added additional exterior, or I should say external capacitance, they became robust against boron 10 events. So again, you know, unless you're really depositing 60 femtocoulombs of charge or something of that order, in general, DRAMs will only be sensitive to the higher energy neutron events. Now, in stark contrast, SRAM, sequential logic, combinatorial logic gates, so anything on your CPU generally will have a very high sensitivity. The linear energy transfer, the threshold for events is typically less than 2, meaning basically the boron 10, the lithium recoil and alpha particle will definitely have potential for upsetting these. All right, so final words. The boron 10 reaction with thermal neutrons produces charge injection in excess of the critical charge of most modern technologies, again, except for DRAM. When alpha contamination has been mitigated, so that's pretty important. We've had situations where there were alpha problems and people were not aware of that. So you have to make sure you definitely don't have no alpha contamination issues. The contribution of thermal neutrons is basically of the same order as that produced by high energy neutrons. And in some cases it can be more, in a lot of cases it's less. And in a few cases I've seen it's almost zero, where the manufacturer has done special, you know, isotopic depositions and things like that. Again, a large amount of boron 10 has been removed from modern IC processes by removing the glass, the boron doped glass. We still have plug and metal barrier formation processes that introduce boron 10 content. So anytime you have a new technology, it's probably a good idea to put it in thermal neutrons just to see, you know, is that going to be a reliability risk for you? And finally, just since there was a discussion of facilities earlier, basically any facilities with the ability to produce high energy, ideally, and thermal neutron fluxes as 2 separate beams. But of course, you can use moderators and things like this to kind of fudge that, will be very useful for the determination of IC response. And again, allow for rapid determination of level of concern. So whether or not you have a boron 10 problem will be obvious very quickly. So that's it for my talk. Hopefully I didn't go over time too much. Thank you very much for your attention.